The universe holds secrets so profound, so baffling, they seem ripped straight from the pages of science fiction. Imagine an object lurking in the cosmic shadows, invisible to our most powerful telescopes, yet so massive it defies the very laws of physics as we know them. These aren't black holes, neutron stars, or any celestial phenomenon we've encountered before. They're something far stranger, something theorists call dark stars. And if they exist, they could rewrite our understanding of the cosmos itself. For centuries, humanity has gazed at the night sky, mapping stars, planets, and galaxies, believing we've uncovered the bulk of what's out there. But what if we've been missing something monumental? Dark stars aren't just another oddity in the vastness of space. They're potential relics from the dawn of the universe, forged in conditions so extreme, they challenge everything we thought we knew about stellar evolution. Unlike ordinary stars which shine through nuclear fusion, these enigmatic giants might be powered by something far more exotic, the annihilation of dark matter itself. Picture a star that doesn't burn, doesn't flicker, but instead thrives in the dark, feeding on the invisible substance that makes up most of the universe's mass. This isn't just theoretical daydreaming. Scientists have spent decades chasing the tantalizing clues that dark stars might be real. From unexplained gravitational anomalies to the strange movements of distant galaxies, the evidence is mounting that something extraordinary is hiding in plain sight. And if we find one, it could unlock answers to some of astrophysics' biggest questions. What is dark matter truly made of? How did the first stars form? Are we on the verge of discovering an entirely new class of celestial objects? This is the frontier of cosmic exploration, where the line between known science and thrilling possibility blurs. So buckle up, we're about to dive into one of the universe's most compelling mysteries, where the darkness might hold the key to everything. To understand these cosmic anomalies, we have to rewind time, way back to the universe's infancy, when everything was hotter, denser, and far more chaotic. In those first moments after the Big Bang, the cosmos wasn't filled with the familiar stars and galaxies we see today. Instead, it was a swirling soup of exotic particles, including dark matter, the mysterious substance that makes up over 80% of the universe's mass. Under those extreme conditions, something extraordinary may have happened. Gravity could have pulled vast clouds of dark matter together so tightly that they collapsed, not into ordinary stars, but into something entirely new, primordial dark stars. These wouldn't be stars as we know them. Modern stars, like our Sun, shine because nuclear fusion transforms hydrogen into helium, releasing energy in the process. But primordial dark stars, they might have burned with a completely different kind of fire. Instead of fusion, they could have been powered by dark matter annihilation, a process where dark matter particles collide and destroy each other, unleashing enormous amounts of energy. Picture a star that doesn't flicker with visible light but glows faintly in other, more elusive ways, hidden in the shadows of the early cosmos. And here's where it gets even wilder. These dark stars wouldn't just be cosmic oddities, they could be the missing link in one of astrophysics' biggest puzzles: how supermassive black holes formed so quickly after the Big Bang. Today, we find these monsters at the hearts of galaxies, weighing millions or even billions of times more than our Sun. But how did they grow so massive so fast? Ordinary stars couldn't have done it alone. Dark stars, however, might have been the perfect seeds because they could grow far larger than any normal star. Some theorists suggest they might have reached masses up to 1 million times that of our Sun. They could have collapsed directly into black holes without ever passing through a supernova. In other words, the very first dark stars may have birthed the very first supermassive black holes, setting the stage for the galaxies we see today. What's even more mind-blowing is that some of these ancient dark stars might still be around. Unlike regular stars, which burn out after a few million or billion years, dark stars could theoretically last much longer. possibly even surviving into the present day, lurking undetected in the vast darkness between galaxies. Finding one would be like discovering a living fossil from the dawn of time, a relic from an era when the universe was still taking its first breaths. So where do we look? Astronomers are scanning the skies for telltale signs, unusual heat signatures, unexpected gravitational lensing, or even strange fluctuations in the cosmic microwave background. It's a needle in a haystack hunt, but if we succeed, the payoff would be nothing short of revolutionary. Uncovering a dark star wouldn't just confirm a wild theory. It would rewrite our understanding of how the universe was built, one dark, ancient giant at a time. Finding these ancient dark stars is like trying to spot a single candle flickering on the moon while standing on Earth. The challenge isn't just their potential rarity, it's that everything about them defies the tools and methods we've relied on for centuries to study the cosmos. Modern telescopes, even our most advanced ones like the James Webb Space Telescope, are designed to detect light visible, infrared, ultraviolet. But what if the object you're searching for doesn't glow in any of these familiar ways? Dark stars, if they exist, would emit almost no visible light. Instead, their energy might come out as faint heat or subtle distortions in the fabric of space-time, signals so subtle they're drowned out by the cosmic background noise of the universe. One major hurdle is their sheer age. If dark stars formed in the early universe, they'd be billions of light years away, their signals stretched and weakened by the expansion of space itself. Imagine shouting across a canyon, only for your voice to fade into a whisper by the time it reaches the other side. Now imagine that canyon is the entire observable universe. Even if these stars are radiating something, that signal could be so shifted toward the far end of the infrared spectrum that it blends into the ambient warmth of space, like trying to hear a single note in a symphony. Then there's the problem of their composition. Ordinary stars leave fingerprints in their light-specific wavelengths absorbed or emitted by elements like hydrogen or helium. But dark stars powered by dark matter annihilation might lack these telltale signatures. Without recognizable chemical footprints, they could be hiding in plain sight, masquerading as dim, unremarkable blips in telescope data. Even their gravitational effects, the way they bend light from objects behind them, might be indistinguishable from other massive but invisible objects like black holes or rogue planets. And here's another twist. Dark stars might not even look like stars. Traditional stars are dense, compact spheres, but theoretical models suggest dark stars could be diffuse, bloated giants spread out over vast distances. Their outer layers might be so tenuous that they're practically invisible, like a ghostly haze rather than a sharp point of light. Telescopes searching for pinpoint sources could easily overlook them, especially if they're drifting in the emptiness between galaxies where we rarely focus our instruments. Yet scientists aren't giving up. New detection strategies are emerging, like hunting for unexpected gamma-ray signatures, the high-energy photons that might be released when dark matter particles annihilate. Others are scouring old telescope data for anomalies, unexplained patches of heat or gravitational lensing events that don't quite fit known objects. There's even talk of designing dedicated instruments to scan for the unique vibrational frequencies dark stars might produce in the cosmic microwave background, the faint afterglow of the Big Bang. The search is a reminder of how much we still don't know. Every time we build a better telescope, we uncover new mysteries, objects, and phenomena that challenge our assumptions. Dark stars could be the ultimate test of our ingenuity, pushing us to rethink not just how we observe the universe, but what we're even looking for, and if we finally spot one. It won't just be a discovery, it'll be a revolution. But what if some dark stars didn't just hide in the shadows? What if they froze in time? Enter one of the most bizarre hypothetical objects in astrophysics, the frozen dark star. Picture a celestial body so cold, it hovers just above absolute zero, the coldest temperature possible in the universe. Unlike typical stars that blaze with heat or even the faint warmth of dark matter annihilation, these relics would be utterly frigid, emitting no detectable light or thermal radiation. They wouldn't just be invisible, they'd be nearly undetectable by conventional means. Yet they could still exert a gravitational pull so strong, they warp the very fabric of space around them, bending light like a cosmic magnifying glass. So how could such an extreme object form? The answer lies in the life cycle of dark stars. While some might persist for billions of years, others could have exhausted their dark matter fuel long ago, cooling over eons until they became stellar ghosts. Without the energy from particle collisions to sustain them, they'd slowly radiate away what little heat remained, freezing into near-perfect darkness. But their mass wouldn't vanish. A frozen dark star could still weigh hundreds or thousands of times more than our Sun, lurking in the void like a trapdoor in space, waiting to betray its presence only through gravity's subtle fingerprints. That's where gravitational lensing comes in. Even if these frozen giants emit no light of their own, their immense mass would distort the path of light passing by, amplifying or warping the images of background galaxies. Astronomers have already used this technique to map dark matter in the universe by observing how unseen mass bends distant starlight. Frozen dark stars, if they exist, could leave similar signatures, tiny anomalies in the night sky where light mysteriously curves around empty patches of space. Imagine looking through a telescope and spotting a distant galaxy that appears strangely stretched or duplicated, with no visible object causing the distortion. That could be the telltale sign of a frozen dark star drifting silently between the stars. The implications are staggering. If these objects are real, they could be hiding in our own galactic backyard, far closer than we think. Interstellar space is vast and mostly empty, making it the perfect hunting ground for cosmic ghosts. Some researchers speculate that frozen dark stars could even account for a fraction of the universe's missing mass, the so-called dark matter we've yet to directly observe. Unlike black holes, they wouldn't swallow light entirely, but their extreme coldness would render them almost as elusive. Detecting them would require a paradigm shift in how we search the skies. Traditional telescopes wouldn't help, but next-generation gravitational wave observatories or ultra-precise lensing surveys might catch their subtle effects. Scientists are already refining models to predict what a frozen dark star's lensing signature would look like. Perhaps a faint, ring-like distortion or an unexplained flicker in a star's brightness as one passes in front of it. Every unexplained gravitational hiccup in the data could be a clue, a whisper from the frozen dark. Yet the hunt is more than just a scientific curiosity. Confirming the existence of these objects would open a new chapter in astrophysics, revealing a previously invisible class of celestial bodies that defy every expectation. They'd challenge our understanding of stellar evolution, dark matter's role in the cosmos, and even the ultimate fate of the universe itself. Are frozen dark stars rare cosmic flukes, or are they lurking everywhere, hidden in plain sight? The answer could change everything if we learn how to see the unseen. Spotting a frozen dark star isn't just a matter of building a bigger telescope, it's about rethinking how we see the universe entirely. Since these cosmic phantoms emit no light and almost no heat, astronomers have to get creative, relying on indirect methods to expose their hiding places. One of the most promising techniques is microlensing surveys, which exploit one of Einstein's most fascinating predictions, that massive objects bend light like a lens. When a frozen dark star drifts in front of a distant background star, its gravity acts like a magnifying glass, briefly amplifying the star's brightness in a telltale spike. These events last mere hours or days, requiring telescopes to scan millions of stars continuously, like watching for a single firefly to flicker in a stadium. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have already used this method to uncover rogue planets and failed stars. but the real prize would be catching a lensing event with no visible object behind it, a flash of light bending around what appears to be empty space. Then there's the hunt for neutrinos, the universe's most elusive particles. While frozen dark stars might not glow, they could still produce a faint trickle of these ghostly particles if residual dark matter annihilation occurs within them. Neutrino detectors like IceCube, buried deep in Antarctic ice, are designed to catch these high-energy messengers from the cosmos. The challenge: neutrinos rarely interact with matter. Trillions pass through your body every second without a trace. Isolating a potential signal from a dark star would be like picking out a single whisper in a hurricane, but it's not impossible. If a pattern emerged, neutrinos streaming from a patch of sky with no known source, it could point to something extraordinary lurking in the void. But why stop there? Some theorists suggest frozen dark stars might leave subtler clues in the cosmic microwave background, the afterglow of the Big Bang. Their immense gravity could create tiny ripples in this radiation, like a pebble disturbing the surface of a pond. Next-generation space telescopes, like the proposed LIGHT-BIRD mission, aim to map these fluctuations with unprecedented precision, turning the entire sky into a dark matter detective's canvas. Even gravitational wave observatories like LIGO could join the search. While frozen dark stars wouldn't collide like black holes, their sheer mass might warp spacetime in detectable ways as they move through galaxies, leaving faint tremors in the cosmic fabric. The beauty of this quest is its unpredictability. Every tool we throw at the problem, lensing, neutrinos, gravitational waves, offers a different lens to peer into the darkness. And if one method fails, another might stumble upon the breakthrough. It's a reminder that the universe rarely hands us answers on a silver platter. Sometimes you have to listen for whispers in the static, chase shadows in the data, and trust that the truth is out there, waiting to be uncovered by those stubborn enough to keep looking. Now imagine a dark star so strange it defies not just astrophysics, but the very rules of reality as we understand them. These aren't just cosmic anomalies, they're quantum nightmares where dark matter doesn't behave like particles at all. Instead, it transforms into something fluid, ghostly, and utterly alien, a Bose-Einstein condensate. Under the right conditions, trillions of dark matter particles could sync up like a cosmic choir, vibrating in perfect unison, their individual identities blurring into a single, eerie quantum wave. The result, a dark star that doesn't just lurk in the shadows, it is the shadow, a colossal entity where matter acts less like solid stuff and more like ripples on an invisible pond. What makes these quantum dark stars so bizarre is their sheer density combined with their surreal behavior. Picture a stellar object the size of a solar system, weighing millions of times more than our sun, yet so diffuse it could pass through ordinary matter like a breeze through a screen door. Unlike the frozen dark stars we discussed earlier, these giants wouldn't just be cold, they'd be quantum cold, existing just a whisper above absolute zero, the temperature where all motion stops. At these extremes, the dark matter inside wouldn't crash together like particles in a normal star. Instead, it would spread out into a single, overlapping quantum state, a phenomenon usually seen only in lab experiments with a few thousand atoms. But scale that up to cosmic proportions, and you've got a star that behaves like a fluid ghost, sloshing and swirling according to the rules of quantum mechanics rather than classical physics. And here's where things get truly mind-bending. Because of their wave-like nature, quantum dark stars could exhibit properties straight out of a sci-fi novel. Gravitational waves passing through them might slow down or scatter as if moving through molasses. Their outer layers could form vast standing waves. Imagine a star with tides that never rise or fall, but freeze in place like a cosmic snapshot. Some models even suggest these stars could tunnel through space, exploiting quantum weirdness to appear to vanish and reappear elsewhere, leaving no trace in between. It's as if the star itself becomes a probability cloud, flickering in and out of existence on a scale that dwarfs entire galaxies. But how could such a thing form? The secret might lie in the earliest moments of the universe, when dark matter was still clumping together in vast primordial clouds. Under the right conditions, extraordinarily low temperatures, and just the right density, these clouds could have collapsed not into compact balls, but into diffuse quantum blobs, held together by gravity yet governed by the uncertainty principle. Unlike ordinary stars, which fight collapse with the outward pressure of nuclear fusion, quantum dark stars would resist squeezing through quantum pressure, a repulsive force generated by the particle's wave-like nature. The result, a star that's both unimaginably massive and paradoxically fragile, a cosmic gel or mold trembling at the slightest disturbance. Detecting these quantum ghosts would require rethinking our entire approach to astronomy. Traditional tools like optical or infrared telescopes would see nothing, but gravitational wave detectors might pick up their subtle tremors. Not the sharp chirps of colliding black holes, but a low, resonant hum, like a bell ringing in slow motion. Alternatively, their wave-like interiors could distort the light of background galaxies in ways unlike anything else, creating lensing effects with telltale interference patterns like ripples in a pond. Some theorists even speculate that quantum dark stars could leave echoes in the cosmic microwave background, subtle fingerprints of their wave-like interactions with the early universe. The implications stretch beyond mere curiosity. If quantum dark stars exist, they'd be living proof that dark matter isn't just a heavier version of ordinary matter. It's something fundamentally different with rules we've only begun to glimpse. They could help solve lingering mysteries like why some galaxies rotate too fast for their visible mass, or why certain gravitational lensing events don't match predictions. Most thrillingly, they'd open a window into quantum physics at scales we've never dreamed of testing, turning the cosmos itself into a laboratory for the bizarre. So while we've yet to find one, the hunt is more than theoretical. It's a challenge to our understanding of reality, a dare from the universe to look deeper, think stranger, and accept that the darkest corners of space might hide truths far wilder than we've imagined. After all, if quantum mechanics can make a single particle exist in two places at once, who's to say it can't do the same to an entire star? Most stars live their lives anchored to galaxies, swirling in vast stellar communities. But what if some dark stars broke free? Imagine a cosmic rebel hurled out into the emptiness between galaxies, drifting alone in the infinite dark. These rogue dark stars wouldn't just be wanderers, they'd be invisible titans warping spacetime as they move, leaving faint but detectable tremors in their wake. The journey of a rogue dark star begins with a violent escape. In the crowded core of a galaxy, gravitational interactions between stars can fling one outward at incredible speeds, a process known as hypervelocity ejection. For ordinary stars, this is rare but not unheard of. For dark stars, though, the stakes are higher. Their immense mass makes them prone to slingshot effects, especially in the chaotic environments near supermassive black holes. One close encounter with a black hole's gravity could send a dark star rocketing into intergalactic space, doomed to drift forever in the freezing void. Out there, far from the light of galaxies, these rogues would become near impossible to spot but not entirely undetectable. Their sheer mass ensures they'd bend spacetime around them, distorting the light of any distant galaxies that happen to lie behind them from our perspective. Astronomers call this phenomenon gravitational lensing, and it's one of the few ways we could uncover these lone giants. Picture a distant galaxy that suddenly appears stretched into a faint ring or arc, with no visible object in front of it to explain the distortion. That eerie signature might be the only clue to a rogue dark star's presence, but there's another, even more subtle way to track them: gravitational waves. When massive objects accelerate or move through space, they create ripples in the fabric of spacetime itself. Current observatories like LIGO are tuned to catch the collisions of black holes and neutron stars, but future detectors could be sensitive enough to pick up the low-frequency waves produced by a lone dark star drifting through the cosmos. Unlike the sharp chirps of merging black holes, these waves would be a slow, steady hum, a cosmic bass note vibrating across billions of light years. The real challenge is distinguishing these signals from the background noise of the universe. Gravitational wave detectors already sift through a sea of interference, everything from seismic tremors on Earth to distant supernova. A rogue dark star's waves might be drowned out unless we know exactly what to listen for. Advanced algorithms and next-generation telescopes could change that, scanning for patterns that match the unique fingerprint of a massive, solitary object in motion. And here's where things get even stranger. Some theories suggest these rogue dark stars could be far more common than we think. If dark matter clumps differently than visible matter, forming vast, invisible halos around galaxies, then countless dark stars might have been born in isolation, never bound to a galaxy at all. They could be wandering the cosmos in numbers we've barely begun to guess, a hidden population of cosmic nomads. Finding one would rewrite the rules. It would prove that dark stars aren't just theoretical oddities, they're real, dynamic objects shaping the universe in ways we're only starting to grasp. More than that, it would force us to rethink how galaxies form and evolve, hinting at a hidden dance of dark matter we've been blind to for centuries. The hunt for rogue dark stars isn't just about spotting invisible objects, it's about mapping the unseen scaffolding of reality itself. Picture a cosmic dance unlike any other, a binary system where one partner shines brilliantly while the other remains utterly invisible. On one side, a familiar star blazing with light and heat. On the other, its dark twin, a shadowy behemoth whose presence is felt only through gravity's relentless pull. This isn't science fiction, it's a tantalizing possibility lurking in the farthest reaches of space, where conventional stars and dark stars could form pairs, locked in an orbital embrace that warps reality itself. The gravitational interplay between these mismatched partners would be nothing short of spectacular. As they spiral around each other, the dark star's immense mass would yank on its luminous companion, stretching and distorting it like tidal forces on an ocean. The visible star might pulse or flicker rhythmically, its light dimming and brightening as the dark star's gravity tugs material from its surface. In extreme cases, this cosmic theft could create vast streams of superheated plasma, arcing through space like a bridge between the seen and the unseen. Telescopes trained on such a system might catch eerie, periodic flares, bursts of X-rays or gamma rays as stolen gas crashes onto the dark star's unseen surface, revealing its presence through violence alone. But the real magic lies in what this duo could teach us. Binary systems are astronomy's Rosetta Stones, decoding the hidden properties of celestial objects through their mutual orbit. By tracking the visible star's path, its speed, wobbles, and deviations, scientists could reverse engineer the dark star's mass, shape, and even hints about its composition. Every slight irregularity in the star's movement would be a clue, a breadcrumb leading us closer to understanding the invisible monster lurking beside it. Gravitational waves add another layer to this cosmic detective story. Unlike pairs of black holes or neutron stars, a dark star binary would produce waves with a unique fingerprint, a slow, asymmetrical undulation caused by the stark contrast between one partner's immensity and the other's near weightlessness. Future observatories tuned to lower frequencies might catch these whispers from the void, revealing duos where only one half of the pair ever flickers into view. Perhaps the most mind-bending possibility lies in their electromagnetic extremes. If the dark star's gravity is strong enough, it could bend the visible star's light into bizarre shapes, Einstein rings, or even duplicate images, like a funhouse mirror on a galactic scale. Imagine a telescope capturing what appears to be two stars where only one should exist, one real and the other a ghostly mirage projected by spacetime's warping. And then there's the question of time. Dark stars, unburdened by the energy losses of conventional stars, could endure for eons, outliving their luminous partners. In the final stages of their dance, the visible star might explode or collapse, leaving the dark star to wander alone, a relic of a partnership that once defied the cosmos's expectations. Until then, their gravitational tango remains one of the universe's most electrifying silent performances, a reminder that the most profound discoveries often lie just beyond the edge of visibility. For astronomers, these binaries aren't just hypothetical, they're potential treasure maps. Spotting one could crack open the enigma of dark matter, proving once and for all that it can clump into stars, not just diffuse halos. It would redefine our understanding of stellar evolution, showing that the universe's building blocks come in forms far stranger than we ever dreamed. The search is already underway, with telescopes scanning star clusters and galaxy peripheries for oddity stars that move as if tugged by unseen hands, or flicker with rhythms no conventional companion could explain. Every anomaly could be a clue, a whisper from the dark side of the cosmos. The beauty of these systems lies in their duality. They're both a revelation and a riddle, offering answers while posing new questions. What happens when dark matter and ordinary matter collide on stellar scales? Can dark stars steal entire atmospheres, leaving their partners as barren husks? Do they forge elements in ways we've never witnessed? Each possibility stretches our imagination, challenging us to see the universe not just as it is, but as it might be, full of shadows dancing just beyond the light. Picture a cosmic predator lurking in the darkness, not a black hole or a neutron star, but something far stranger. A dark star locked in a deadly embrace with an ordinary star, slowly draining its life away. This isn't just gravity at work, it's a feeding frenzy on a stellar scale, where the dark star's immense pull strips gas from its companion, creating a swirling vortex of superheated plasma. As this stolen matter spirals inward, it doesn't vanish into darkness. Instead, it heats up to millions of degrees, unleashing bursts of high-energy radiation, X-rays and gamma rays flickering like a faint, eerie beacon in the void. The process is as mesmerizing as it is violent. Unlike black holes, which famously let nothing escape, dark stars might allow some of this stolen energy to leak back into space. The accretion disk, a glowing ring of doomed material, could glow faintly in wavelengths our telescopes strain to detect. Imagine a star that doesn't just hide in shadows but wears them like a cloak, its presence betrayed only by the death throes of the matter it consumes. What makes this scenario even more compelling is the sheer timescale involved. A dark star could feed for billions of years, far outliving the lifespan of its companion. The visible star might eventually wither, its outer layers peeled away until only a dense core remains, a white dwarf or neutron star left orbiting its dark counterpart like a cosmic ghost. In some cases, the dark star's appetite could even trigger cataclysmic explosions, as the buildup of stolen matter reaches critical limits, igniting runaway thermonuclear reactions. Detecting these vampiric duos wouldn't be easy, but astronomers have clues to guide them. Systems where a visible star orbits an unseen partner with inexplicable speed or wobble could be prime candidates. Some might flicker with unexpected X-ray flares, their timing too precise to be random. Others could show strange chemical signatures in their light, elements like helium or carbon enriched by the dark star's gravitational stripping, a telltale sign of stellar cannibalism. The implications stretch beyond mere curiosity. If dark stars can siphon matter so efficiently, they might explain some of the universe's most energetic phenomena, mysterious gamma-ray bursts or ultra-luminous X-ray sources that defy conventional explanations. They could even serve as dark matter detectors in their own right, their feeding habits revealing clues about how dark matter interacts with ordinary particles under extreme conditions. Yet the most tantalizing possibility is what happens when the feast ends. A dark star gorged on stellar material might undergo drastic changes, collapsing into a black hole, flaring as a temporary quasar, or even triggering the formation of exotic hybrid objects unlike anything we've seen. Every X-ray flicker, every distorted orbit is a breadcrumb leading us closer to understanding the darkest corners of the cosmos, where stars don't just die but are devoured. At the heart of our galaxy, hidden behind swirling clouds of dust and the glare of a million stars, sits a gravitational monster, Sagittarius A, the supermassive black hole anchoring the Milky Way. Or does it? What if the true ruler of our galactic core isn't a black hole at all, but something far more enigmatic, a supermassive dark star, cloaked in shadow and distorting the very fabric of space around it? The idea isn't pure fantasy. For decades, the behavior of Sagittarius A has puzzled astronomers. While it fits many black hole predictions, its immense gravity bending light, its presence revealed by stars whipping around an invisible point, there are odd gaps in the story. Black holes are thought to be messy eaters, heating infalling gas to blistering temperatures and blasting out radiation as material vanishes beyond the event horizon. Yet Sagittarius A is strangely quiet, emitting far less energy than expected for an object of its size. Some researchers argue this could hint at an alternative explanation, a dark star, not a black hole, lurking at the galactic center. Unlike a black hole which traps everything inside its event horizon, a supermassive dark star might behave differently. Instead of swallowing matter entirely, it could allow some energy to escape, not as the violent jets seen in active black holes, but as subtle, diffuse emissions. Picture a cosmic engine running on dark matter annihilation rather than accretion, producing faint ripples of energy detectable only as anomalies in the galactic core's heat signature. These emissions wouldn't match the X-ray flares or radio waves we associate with black holes, offering a possible explanation for Sagittarius A's unexpected silence. Then there's the mystery of the missing disk. Most supermassive black holes are surrounded by a thick, glowing ring of gas and dust, the accretion disk where material spirals inward. Sagittarius A's disk, however, is strangely faint and patchy. A dark star could explain this too. Without the relentless pull of a black hole's singularity, infalling matter might not compress and heat as dramatically. Instead, it could form a looser, cooler structure or even be repelled by the dark star's unique physics, creating gaps and asymmetries in the disk that defy conventional models. But the most tantalizing clue lies in the orbits of nearby stars. For years, astronomers have tracked S-stars, fast-moving bodies circling Sagittarius at dizzying speeds. Their paths map out the gravitational field of the central object, and while they mostly align with black hole predictions, there are subtle deviations. Some stars exhibit unexpected wobbles or shifts in their trajectories, as if tugged by invisible structures. A dark star's gravity could produce these anomalies, especially if its mass isn't concentrated in a single point but spread out in a diffuse, wave-like halo, something purely theoretical for now, but not impossible if dark matter behaves in ways we don't yet understand. The implications are staggering. If the Milky Way's core harbors a dark star instead of a black hole, it would upend our understanding of galaxy formation. Supermassive black holes are thought to be the anchors around which galaxies assemble, their gravity shaping stellar orbits and regulating star birth. But a dark star could fulfill the same role while operating under entirely different rules, ones we're only beginning to grasp. It might explain why some galaxies lack the bright, active cores seen in others, or why certain black hole candidates don't emit the expected radiation. Proving this hypothesis won't be easy. Detecting a dark star in the galactic core would require instruments sensitive to the most elusive signals, perhaps faint gravitational waves from its oscillations or patterns in the cosmic microwave background distorted by its presence. Future telescopes like the upcoming LISA Gravitational Wave Observatory or advanced neutrino detectors might finally provide the evidence needed to settle the debate. Until then, the question lingers, is Sagittarius the black hole we've always assumed, or is it something far stranger, a dark star, a cosmic imposter hiding in plain sight? The answer could rewrite not just the story of our galaxy, but the very nature of the universe's most mysterious objects. After all, in the darkest corners of space, reality often proves far more inventive than our wildest theories. Deep in the cosmic voids, far from the blazing light of ordinary stars, lie regions of space so dense with dark matter they could serve as the universe's most secretive stellar nurseries. Unlike the glowing clouds of gas and dust where regular stars are born, these hidden cradles operate in total darkness, sculpted by forces we're only beginning to understand. Imagine a vast, invisible web of dark matter filaments, cosmic highways where phantom particles outnumber atoms 100 to 1. Where these threads knot together, gravity could work its silent magic, compressing dark matter into cores so dense they ignite not with nuclear fire, but with the eerie glow of particle annihilation. What makes these nurseries fundamentally different is their architecture. Ordinary stellar nurseries like the Orion Nebula shine brightly because collapsing gas heats up, triggering fusion. But in dark matter halos, those massive, diffuse spheres enveloping galaxies, the physics flips entirely. Without electromagnetic interactions to create friction or light, dark matter collapses more smoothly, like ink dispersing in water. Simulations suggest these halos could harbor substructures called dark matter clumps, regions where the density spikes enough to form primordial dark stars. Some theories propose they'd need a seed of regular matter to kickstart the process, a single hydrogen atom acting as the grain of sand around which an invisible pearl forms. The birth process would be chillingly slow. While normal stars form over millions of years, dark stars might take billions, their growth governed by the sluggish decay of dark matter particles. Instead of the turbulent, glittering chaos of a nebula, these nurseries would be eerily placid, no stellar winds, no shock waves, just the gradual accumulation of shadow. And the scale defies imagination. A single dark star nursery could span thousands of light years, dwarfing even the largest molecular clouds we know. Yet the most fascinating difference might be their longevity. Traditional stellar nurseries fade as radiation blows away their gas, but dark matter halos persist for eternity. This means dark stars could be forming right now in the Milky Way's outskirts, hidden in the halo that stretches 10 times farther than our visible disk. Future telescopes tuned to gravitational lensing or neutrino emissions might catch these nurseries in the act, revealing not just individual dark stars, but the shadowy factories where they're forged. The implications stretch beyond astronomy. If these nurseries exist, they'd prove dark matter isn't just a passive scaffold for galaxies, it's an active participant in cosmic evolution, capable of birthing entirely new classes of objects. Who knows what other unseen wonders might be taking shape in the darkness? Now picture this: a dark star spinning so fast it becomes a cosmic metronome, pulsing not with light, but with ripples in space-time itself. Unlike ordinary pulsars that blast beams of radiation across the universe, this phantom pulsar would be silent in every wavelength we know, its rhythm detectable only through the faint tremors it sends through the fabric of reality. Gravitational waves would be its language, each rotation a steady drumbeat echoing across billions of light years, invisible yet unmistakable to those who know how to listen. What sets these phantom pulsars apart is their sheer strangeness. Traditional neutron stars pulse because their magnetic fields funnel energy into narrow beams, sweeping across space like a lighthouse. But a dark star has no magnetic field, no scorching surface, no furious jets of particles. Instead, its power comes from raw, unbalanced mass, a lopsided behemoth wobbling as it spins, its imperfections warping spacetime with every turn. Imagine a skater pulling their arms in, spinning faster and faster. except this skater is a city-sized monster weighing more than our sun, and the ice is the universe itself bending under its weight. Detecting these dark pulsars would require a revolution in how we observe the cosmos. Current gravitational wave observatories like LIGO are tuned to catch the violent crashes of black holes and neutron stars, sudden, catastrophic events that send shockwaves through spacetime. But a phantom pulsar signal would be different. A low, steady hum, a nearly perfect sine wave rising and falling with clockwork precision. It's the difference between hearing a thunderclap and the distant, rhythmic ticking of a grandfather clock. Future detectors like the proposed Einstein telescope or the space-based LISA mission could be sensitive enough to pick up these whispers. Their ultra-precise instruments might catch the subtle shifts in frequency as the dark star's spin slows over millennia, its energy bleeding away into the void as gravitational ripples. The real challenge lies in distinguishing these signals from the universe's background noise. Gravitational wave astronomy is still in its infancy, and every new detection teaches us how much we've been missing. A phantom pulsar's waves could easily blend into the cacophony of merging black holes, supernova, and even the residual echoes of the Big Bang. But advanced algorithms are already being trained to sift through the data, searching for patterns that match the unique fingerprint of a spinning dark star, a signal so regular it might at first be mistaken for a glitch in the machines. And here's where the mystery deepens. If we find one, it could rewrite the rules of stellar evolution. Spinning dark stars shouldn't exist under current models. Their formation would require conditions so extreme they border on the impossible. Did they emerge from the chaos of the early universe, where dark matter clumped in ways we can't yet simulate? Or are they the remnants of some cataclysmic encounter, a dark star stretched and twisted by a close brush with a black hole? Each pulse would carry clues, a cipher waiting to be decoded. The implications stretch far beyond astrophysics. Phantom pulsars could be the universe's most precise timekeepers, their spins so stable they rival atomic clocks. Future civilizations might use them as navigation beacons, triangulating their position in the galaxy by the rhythms of the unseen. They could even test Einstein's theory of relativity to breaking point. If their waves deviate from predictions, it might hint at new physics, at forces beyond gravity itself. So while we've yet to detect one, the hunt is already reshaping how we see the cosmos. It's a reminder that the universe's greatest secrets don't always announce themselves with fireworks. Sometimes they're hidden in the quietest vibrations, the faintest trembles of space-time, waiting for the right moment and the right listener to reveal them. Every star meets its end, even the most enigmatic ones. For dark stars, death doesn't mean fading into obscurity. Instead, their final act could be a transformation into something even more bizarre, an exotic remnant defying the known laws of physics. Picture a dark star having exhausted its supply of dark matter fuel, no longer able to sustain itself against the crushing weight of its own gravity. The collapse wouldn't be a quiet fade, it might spark a metamorphosis, forging an object unlike anything we've ever witnessed. One possibility is the dark neutron star, a hypothetical corpse where the rules of conventional stellar remnants don't apply. Ordinary neutron stars are already extreme city-sized spheres so dense that a teaspoon of their material outweighs a mountain. But a dark neutron star would take that strangeness to another level. Instead of being packed with neutrons, its core could be crammed with a shadowy analog dark matter particles compressed into a degenerate state we can scarcely imagine. Without the electromagnetic repulsion that keeps ordinary neutron stars from collapsing further, these remnants might reach densities that flirt with the boundaries of known physics. Some theories even suggest their cores could harbor pockets of quark-gluon plasma, a primordial soup of particles not seen since the universe's first microseconds. Then there's the quark dark star, an object where dark matter doesn't just collapse, it shatters into its most basic constituents. In ordinary stars, matter stops at neutrons under extreme pressure. But if dark matter is made of something more fundamental, particles like actions or WIMP, their breakdown could birth a star composed entirely of free-floating quarks. These wouldn't be the quarks we know, they'd be shadowy counterparts interacting only through gravity and whatever feeble forces govern dark matter. The result, a bizarre, ultra-dense orb where gravity and quantum weirdness battle for dominance, possibly even stabilizing the star against total collapse. The aftermath of a dark star's death could rewrite the cosmic rulebook. Unlike black holes which trap everything behind an event horizon, these remnants might allow some energy to escape not as light, but as subtle gravitational murmurs or faint bursts of hypothetical dark radiation. Their sheer density could warp spacetime in peculiar ways, creating gravitational lenses that flicker unpredictably or emitting low-frequency waves detectable only by future observatories. Some models even suggest they could form crystalline structures, their interiors arranged in lattice-like patterns that vibrate at frequencies beyond anything in nature. But the most tantalizing question is whether these remnants could still interact with the visible universe. A dark neutron star might occasionally siphon gas from a passing cloud, its gravity igniting bursts of radiation as ordinary matter crashes onto its invisible surface. A quark dark star, if it accumulates enough baryonic matter, could develop a thin crust of normal material, a shell of neutrons or exotic atoms masking the unfathomable darkness beneath. These hybrids would blur the line between dark and light, offering a bridge to study the invisible through the distortions it leaves on the familiar. The hunt for such objects is already producing eerie candidates. Astronomers have spotted neutron stars with inexplicable properties, some too cold, others too massive, as if an unseen hand tweaked their physics. Could these be dark star remnants in disguise? The answer might lie in gravitational wave astronomy. When these exotic corpses collide, their mergers wouldn't produce the same chirps as black holes or neutron stars. Instead, their waves might carry subtle fingerprints, anomalies in frequency or duration, hinting at interiors made of something far stranger. Ultimately, dark star remnants challenge us to rethink stellar death itself. The universe has a habit of surprising us, turning theoretical curiosities into observable phenomena. If these cosmic ghosts exist, they're not just dead stars, they're windows into a hidden layer of reality, where the darkest corners of physics play out on a scale beyond comprehension. And somewhere out there, in the silence between the stars, one of these relics could be waiting its secrets locked in the weight of its own collapse, daring us to listen. What if dark stars aren't just made of dark matter? What if they're built from something even stranger, something that belongs to an entirely different universe? Enter the most speculative and mind-bending idea yet: mirror dark stars, celestial bodies composed of mirror matter, a hypothetical substance that could be the shadowy twin of everything we know. In this radical theory, mirror matter isn't just another flavor of dark matter. It's a parallel version of ordinary atoms, obeying its own set of physical laws, possibly even forming its own periodic table of elements. These wouldn't just be stars hiding in the dark, they'd be cosmic doppelgangers, entire worlds made of matter that barely acknowledges our universe exists. The concept emerges from one of physics' most tantalizing what-if scenarios, that nature has a hidden symmetry, a mirror version of reality where every proton, electron, and quark has a counterpart. These mirror particles would interact through mirror forces, their own version of electromagnetism and nuclear interactions, but would be nearly blind to our universe's forces. The only bridge between the two realms, gravity, that means a mirror dark star blazing with mirror fusion and emitting mirror photons, would be as invisible to us as a ghost, except for the way its mass bends space and tugs on visible stars. Imagine a star system where the Sun isn't alone, where an identical, inverted twin orbits beside it, unseen and untouched. the mirror star might have its own planets, its own chemistry, even its own life, all locked away in a parallel dimension of matter. From our perspective, it's just a gravitational anomaly, a patch of space that behaves as if something massive is there, yet our telescopes show nothing. The only hints might come from subtle distortions, light bending around empty space, stars wobbling as if tugged by an invisible companion, or unexplained gaps in the cosmic microwave background where mirror radiation subtly leaks through. What makes this idea so electrifying is how it upends the search for dark matter. If mirror dark stars exist, we wouldn't just be hunting for clumps of unseen particles, we'd be probing the edges of a whole other reality. Some theories suggest these stars could collide with ordinary matter, not in fiery explosions, but in eerie, silent mergers where the two types of matter pass through each other like mist, their only interaction a faint ripple in space-time. Other models propose that mirror matter could clump differently under gravity, forming fractal-like structures or vast, diffuse clouds that defy conventional astrophysics. The kicker, mirror dark stars might solve mysteries that have baffled scientists for decades. Take neutron stars, for example. Some spin faster than physics should allow, as if an unseen force is nudging them. Could a mirror star be the culprit, its gravity subtly transferring energy across the dimensional divide? Or consider dark matter's uneven distribution in galaxies. What if it's not a smooth halo but a network of mirror star remnants, their invisible mass sculpting the cosmos from the shadows? Detecting them would require a leap in how we observe the universe. Traditional telescopes are useless, but gravitational wave detectors might catch the vibrations of a mirror star quake or the tremors of a mirror black hole's birth. Particle colliders could hunt for rare, high-energy events where mirror particles briefly flicker into our reality. Even quantum experiments searching for fifth forces, subtle deviations from Newton's gravity at tiny scales, might stumble upon evidence of mirror matter's faint gravitational whispers. The implications spiral outward like ripples in a pond. If mirror dark stars are real, they'd prove our universe is just one layer of a far grander multiverse, where every galaxy, every star, every atom has a hidden twin. They'd force us to rewrite the rules of cosmology, not just to include dark matter, but to account for an entire shadow cosmos woven into the fabric of our own. And somewhere out there, in the depths of space, an invisible sun might be burning with a light we'll never see, a beacon from a world that mirrors our own, yet remains forever just out of reach. The hunt for these phantoms is more than scientific curiosity. It's a test of how deeply we're willing to question reality. After all, if the universe can hide entire stars made of matter we can't touch or see, what else is lurking in the darkness, waiting to rewrite the story of everything? A dark star doesn't just rewrite the rules of stellar physics, it could host an entire shadowy planetary system where worlds orbit in perpetual night. Picture a planet circling this invisible giant, basking not in sunlight but in the faint, residual warmth of dark matter annihilation. Without the fierce glow of a traditional star, such a world wouldn't experience day or night, just an eternal twilight where heat seeps from the planet's core and the dark star's whisper of energy. This isn't science fiction, it's a chilling possibility that could expand our understanding of where life might thrive in the cosmos. The first puzzle is how such a planet could stay warm enough to support life. On Earth, sunlight drives our climate and fuels photosynthesis, but a dark star's planet would rely on entirely different mechanisms. One possibility is tidal heating, the same force that keeps Jupiter's moon Io volcanically active. If the planet's orbit is elliptical, the dark star's gravity would stretch and compress its interior, generating friction and heat. Imagine a world with oceans warmed not by sunlight but by the constant churning of its own molten core, its surface dotted with geothermal vents spewing minerals into inky black seas. These hydrothermal systems could mirror the extreme environments on Earth where life thrives without sunlight. like the ecosystems around deep sea vents teeming with tube worms and bacteria. Then there's the dark star itself. While it wouldn't radiate visible light, the annihilation of dark matter particles in its core could produce a trickle of other energies, gamma rays, neutrinos, or even exotic particles we've yet to discover. A planet with a thick, insulating atmosphere might trap this faint radiation, creating a greenhouse effect that stabilizes temperatures. Alternatively, the planet's own internal heat, left over from its formation or maintained by radioactive decay, could sustain subsurface oceans beneath miles of ice, much like Saturn's moon Enceladus. Life here wouldn't need a sun, it would evolve in the slow, steady warmth of the planet's own hidden furnace. But what would this life look like? In the absence of sunlight, photosynthesis would be impossible, forcing organisms to rely on chemosynthesis, extracting energy from chemical reactions, like the bacteria that thrive in Earth's darkest caves. Ecosystems might cluster around geothermal hotspots, their food chains built on microbes that metabolize sulfur or hydrogen. Predators could evolve to detect prey through subtle vibrations or bioelectric fields, their eyes atrophied over generations in favor of heightened senses for sound, touch, or even magnetic fields. Some theorists suggest such life might develop bioluminescence, creating its own eerie glow to communicate or lure prey in the endless dark. The implications for astrobiology are profound. If life can exist around a dark star, the habitable zones of the universe expand dramatically. No longer confined to the narrow bands around sun-like stars, life could arise in the most unexpected places, drifting in the voids between galaxies or orbiting rogue dark stars untethered to any cosmic neighborhood. It raises spine-tingling questions. Could dark planets outnumber conventional ones? Are we surrounded by invisible biospheres, thriving in the shadows just beyond our perception? Detecting these worlds would require rethinking our search strategies. Traditional planet hunting methods, like watching for a star's dimming as a planet transits, won't work when the star itself is invisible. Instead, astronomers might look for gravitational microlensing events, brief brightening of background stars as a dark star's planet warps space-time. Or they could hunt for unexplained infrared signatures, heat leaking from a hidden world surface. Future telescopes like NASA's and Nancy Grace Roman Space Telescope could be sensitive enough to spot these faint clues, peeling back the veil on an entirely new class of exoplanets. The most haunting possibility, these planets might not be lifeless at all. They could harbor civilizations advanced enough to harness dark energy or navigate by gravitational waves, their existence utterly alien to our own. While that remains speculative, the mere idea forces us to confront how little we truly know about the universe's potential for life. After all, if creatures can thrive in Earth's most hostile corners, why not on a world where the sun never rises? The darkness, it seems, might not be empty, just waiting to be understood. Some stars don't fade quietly, they go out with a bang that shakes the cosmos to its core. Now picture a dark star reaching its catastrophic breaking point, its core overwhelmed by the crushing weight of accumulated dark matter. This wouldn't be an ordinary supernova, it would be a detonation of pure darkness, unleashing a storm of invisible radiation and gravitational tremors unlike anything we've ever witnessed. The collapse begins with a whisper, as the dark star exhausts its fuel, no longer able to sustain itself through particle annihilation. Gravity takes over, compressing its core beyond the limits of physics as we know it. Unlike conventional stars, which explode when fusion falters, a dark star's demise would play out through forces we can't directly observe. The implosion might trigger a runaway chain reaction, where collapsing dark matter particles collide with such violence that they annihilate en masse, converting their hidden energy into a burst of high-energy dark radiation. Imagine a shock wave rippling outward, not as light, but as a pulse of gravitational distortion and exotic particles, a silent tsunami bending the fabric of spacetime itself. Compare this to the supernova we're familiar with, a typical dying star lights up the galaxy, outshining entire galaxies for weeks as it scatters heavy elements across space. But a dark star's explosion would leave no visible fireworks, just subtle ripples in the cosmos. Telescopes wouldn't see a brilliant flash, but gravitational wave detectors might register a sharp, asymmetric chirp followed by an eerie fade. Nearby objects could be showered with mysterious high-energy particles, while any orbiting planets might experience sudden, unexplained heating, like standing near an invisible bonfire. The most striking parallel might be to gamma-ray bursts, the universe's most powerful explosions. These ultra-energetic events beam focused jets of radiation across billions of light-years. A dark star's death could produce something eerily similar, but instead of gamma rays, it might emit focused streams of dark photons or weakly interacting massive particles. If one of these jets happened to point at Earth, we might detect it as a spike in neutrinos or an anomaly in dark matter detectors, a fleeting clue that something monumental had occurred in the void. What makes this phenomenon so thrilling is its potential to rewrite cosmic history. Astronomers have long puzzled over unexplained bursts of energy that don't fit known supernova or gamma-ray burst models. Could some of these be the fingerprints of dying dark stars? Future observatories tuned to gravitational waves or dark matter interactions might finally catch one of these explosions in the act, revealing a hidden chapter of stellar evolution. The darkness, it seems, has its own way of going supernova, and we're only beginning to learn its language. Globular clusters have always fascinated astronomers, tightly packed spheres of stars, some containing hundreds of thousands of suns bound together by gravity. But what if we've been missing half the picture? Hidden among these glittering stellar cities might be something far stranger, an entire cluster where not a single star shines. A dark star cluster, an assembly of invisible giants, their presence betrayed only by the way they warp the space around them. Picture the scene, a dense, spherical swarm of dark stars, each one a behemoth hundreds or thousands of times more massive than our Sun, all orbiting a shared center of gravity. Without the glare of fusion-powered light, this cluster wouldn't show up in any optical, infrared, or ultraviolet survey, but its influence would be undeniable. The combined gravitational tug of so much unseen mass would yank on nearby visible stars, sending them whipping around empty space as if pulled by an unseen hand. Astronomers tracking these stars would notice their paths don't make sense, like watching a dance where half the partners are ghosts. The evidence might already be hiding in plain sight. Take Omega Centauri, one of the Milky Way's most massive globular clusters. Some of its stars move in ways that defy predictions, as if extra mass is lurking where telescopes see nothing. Current explanations lean toward intermediate black holes or dense pockets of dark matter, but a dark star cluster offers another compelling answer. Instead of a single invisible object warping orbits, it could be dozens or hundreds of them, each adding its own subtle pull to create a gravitational fingerprint unlike anything else in the cosmos. Detecting such a cluster would require piecing together clues from multiple observations. Precise measurements of star movements could reveal areas where gravity is stronger than expected, mapping out the unseen mass's distribution. Gravitational lensing might expose the cluster's outline as background starlight bends around it in a telltale pattern. Even the cluster's heat signature could give it away. While dark stars don't radiate visible light, their dark matter annihilation could produce faint infrared glows like embers in the cosmic dark. The implications would rewrite astrophysics. If dark stars can form clusters, it suggests they're not rare flukes but a fundamental part of galactic evolution. These hidden structures could be the universe's silent architects, shaping the growth of galaxies from the shadows. Some might even predate their visible counterparts, forming in the primordial darkness before the first ordinary stars ignited. And if they're out there, they're proof that the cosmos is far stranger and far richer than we ever imagined. the search isn't just about filling in missing mass, it's about uncovering an entire invisible stellar ecosystem waiting to be explored. Among the strangest hypothetical dark stars, one variant stands out not for its mass or temperature, but for an invisible force that could make it a cosmic lighthouse, an intense, seething magnetic field. Unlike ordinary magnetars which blast X-rays across the galaxy, this magnetic dark star would wield its power silently, warping the fabric of space in ways we're only beginning to theorize. Picture a stellar object where dark matter isn't just passively clumped together, but twisted into frenzied, swirling currents, generating magnetic fields thousands of times stronger than anything in known physics. The result, a phantom dynamo crackling with dark energy, its influence rippling far beyond the star itself. What makes this scenario plausible is dark matter's potential complexity. While we often imagine it as inert, collisionless particles, some theories suggest certain dark matter types could carry subtle electromagnetic interactions, not enough to glow, but enough to create currents under extreme conditions. In the churning core of a dark star, where densities reach unimaginable levels, these particles might align like iron filings around a magnet, amplifying their collective force until the entire object becomes a celestial electromagnet. The field wouldn't produce visible auroras or solar flares. Instead, it might warp the quantum vacuum around the star, sporadically ejecting bursts of dark photons, hypothetical particles that could manifest as faint radiostatic or distortions in the cosmic microwave background. The observational clues would be maddeningly subtle. Radio telescopes might catch fleeting, unexplained pulses, not the rhythmic beats of a pulsar, but erratic bursts resembling cosmic interference. The star's magnetic grip could also leave fingerprints on nearby matter. Gas clouds drifting too close might suddenly ionize, their particles whipped into unusual configurations without an obvious energy source. Even the cosmic microwave background, the universe's oldest light, could bear scars from such an object. As the dark star's field fluctuates, it might imprint faint, ring-like anomalies in the microwave haze, like ripples from a stone tossed into a pond we can't see. Then there's the gravitational lensing twist. A magnetic dark star's field could theoretically warp spacetime itself, adding an extra layer of distortion to its already formidable gravity. Light passing near it wouldn't just bend, it might twist, creating spiral patterns in the images of background galaxies. This effect, called gravitational Faraday rotation, has never been observed around any known object. Spotting it would be like finding a cosmic fingerprint, proving that something unprecedented lurks in the darkness. The implications stretch beyond astrophysics. If magnetic dark stars exist, they'd force us to rethink dark matter's fundamental nature, suggesting it's not just a passive scaffold but an active, dynamic player in cosmic evolution. They could also explain lingering mysteries, like the origin of certain high-energy radio bursts or the uneven distribution of the microwave background's polarization. Most tantalizingly, they might serve as bridges between the visible and invisible universe, not just hiding in the shadows, but actively shaping the light we can see. Detecting one would require a paradigm shift in observation strategies. Instead of scanning for light, astronomers would need to correlate anomalies across multiple wavelengths, radiostatic paired with gravitational lensing, or microwave distortions aligned with neutrino spikes. Next-generation telescopes like the Square Kilometre Array, with its unparalleled radio sensitivity, might be the key to catching these phantoms in the act. The hunt is more than academic. Magnetic dark stars represent a frontier where known physics blurs into speculation, where the universe's darkest corners might crackle with invisible energy. They remind us that the cosmos doesn't just conceal its secrets, it sometimes whispers them in a language we're still learning to hear. At the far edge of what physics allows, there could exist a dark star so unimaginably massive that it twists time itself. This isn't just an object lurking in the shadows, it's a cosmic time machine where gravity's pull is so intense that clocks near its surface would tick infinitely slower than those on Earth. Welcome to the realm of the time-dilated dark star, a gravitational leviathan where the universe's most mind-bending relativistic effects become everyday reality. The key to this phenomenon lies in Einstein's theory of general relativity, which tells us that massive objects don't just bend space, they stretch time. Near a black hole's event horizon, this effect becomes extreme, with time slowing to a crawl for an outside observer. But a dark star with similar mass, yet no event horizon, could achieve something equally bizarre without fully crossing the point of no return. Imagine a star so dense that light struggling to escape its surface loses tremendous energy, redshifting into near oblivion. A single hour near its surface could equate to years passing elsewhere in the galaxy, creating a pocket of the cosmos where time itself runs at a whisper. Observing such an object from Earth would be like watching a cosmic slow-motion reel. Gas spiraling toward the star's surface would appear to freeze mid-plunge, its final descent stretched across decades of our time. Any dim flickers of radiation escaping its grip would arrive at our telescopes stretched into long, low-frequency waves, as if the star's whispers were being dragged through molasses. Even more unsettling, the star's gravitational lensing, the way it bends light from objects behind it, would create warped, smeared images as though the fabric of space-time around it were stuck in tar. The real challenge for astronomers would be distinguishing this slowdown from other cosmic oddities. A time-dilated dark star's light signature might mimic a super slow-motion black hole or an oddly cold neutron star. But subtle clues could give it away, like the absence of an accretion disk's telltale X-ray glow, or gravitational waves with a peculiar, drawn-out frequency. Future telescopes capable of tracking individual photons over centuries might catch the star's light gradually dimming as time dilation's grip tightens, a fade-out spanning human lifetimes. The implications ripple beyond mere curiosity. If such an object exists, it would serve as a natural laboratory for testing relativity's limits, offering a front-row seat to effects usually observable only near black holes, but without the inescapable singularity. It could also rewrite the rules for dark matter's behavior under extreme conditions, revealing whether it too bends to time's whims. Most tantalizingly, it might hint at a hidden population of almost black holes, objects teetering on the edge of collapse, frozen in cosmic hesitation. Finding one would demand patience worthy of the star's own time-warped nature. Astronomers would need to scour decades of data for objects that change too slowly or too little, their very stillness betraying them. It's the ultimate cosmic hide and seek, where the prize isn't just a new class of star, but a glimpse into gravity's most surreal domain where time itself becomes fluid and darkness holds the universe's clock. A dark star hiding in the depths of a dark nebula isn't just invisible, it's the universe's ultimate hide-and-seek champion, wrapped in layers of cosmic camouflage. Imagine an object already undetectable by conventional means, then draped in a shroud of swirling dark matter and dust so thick, even the faintest traces of its presence are smothered. This isn't merely a star that doesn't emit light, it's a shadow within a shadow, a void so complete it defies observation. The first challenge in spotting such an object lies in the nature of dark nebulae themselves. These aren't the glittering stellar nurseries we often picture, but dense, cold clouds where dust and gas blot out all background light. Inside them, temperatures plunge near absolute zero, and particles move sluggishly, creating an environment where even the slightest thermal signature, like the residual heat from dark matter annihilation, could be absorbed before it escapes. It's like trying to detect a whisper in a hurricane. The signal drowns in the noise of the nebula's own frigid embrace, yet astronomers aren't completely unarmed. One promising avenue is gravitational microlensing, watching for subtle distortions in the light of stars behind the nebula. A dark star's mass would warp space-time, bending those distant pinpricks into momentary brightening or splitting as they pass through its hidden gravitational field. The trick is distinguishing these events from the nebula's own chaotic dust clumps, which can mimic lensing effects. Advanced algorithms now sift through mountains of telescope data, hunting for anomalies that move too fast to be mere dust, their patterns hinting at a single, massive object lurking within. Another clue might come from cosmic rays, high-energy particles that ricochet through space. As these rays collide with the nebula's dark matter halo, they could produce faint showers of secondary particles like sparks striking flint. Detectors like the Alpha Magnetic Spectrometer aboard the International Space Station are fine-tuned to catch these rare interactions. If a dark star sits at the nebula's heart, its concentrated dark matter could create an unusual spike in particle collisions, tracing an invisible bullseye in the data. Then there's the cold, quiet glow of molecular hydrogen. Dark nebulae are rich in this simple molecule, which emits minuscule amounts of radio waves even in freezing conditions. A dark star's gravity would stir the nebula's gas, creating turbulence that subtly alters these radio emissions. Radio telescopes like ALMA could map these disturbances, revealing the telltale swirl of an unseen mass disturbing the cosmic pond. It's akin to watching ripples on a lake's surface to locate something moving beneath. Only here, the ripples are whispers of radiation, and the depths are light years thick. Perhaps the most tantalizing possibility lies in neutrino astronomy. These ghostly particles, born in the hearts of stars and cataclysmic events, barely interact with matter, slipping through nebular dust like it isn't there. A dark star, even one veiled by a nebula, might emit neutrinos from residual dark matter interactions in its core. Detectors like Ice Cube in Antarctica could, in theory, catch these faint trails, triangulating their origin back to a patch of seemingly empty space. The signal would be achingly subtle, a handful of excess neutrinos amid a sea of background noise, but if confirmed, it would be like hearing a heartbeat through a concrete wall. The hunt for these doubly hidden giants is more than an astronomical challenge, it's a test of creativity. Every tool in our arsenal, from gravitational waves to particle physics, must be pushed to its limits. And if we succeed, the reward isn't just finding a dark star, but proving that no shadow, no matter how deep, can hide forever from the relentless curiosity of science. After all, the universe loves to play hard to get, but it always leaves clues for those who know how to look. Among the myriad possibilities for dark matter, one candidate stands out as both a leading theory and a potential key to unlocking the mystery of dark stars, weakly interacting massive particles, or WIMP. These hypothetical particles, though never directly observed, are among the most compelling explanations for dark matter's gravitational effects. Now, imagine a star forged not from atoms, but from these elusive WIMP, a celestial body so dense with them that their collisions ignite a slow, smoldering annihilation, powering the star in a way that defies conventional physics. Unlike ordinary stars which shine through nuclear fusion, a WIMP star would glow faintly from the energy released as its dark matter particles collide and destroy one another. This process wouldn't produce the dazzling light we associate with stars, but it might generate something just as revealing: high-energy neutrinos or gamma rays, the universe's quiet messengers. These signals could be our best hope for detecting such a star, offering a glimpse into a realm where dark matter isn't just an invisible halo, but the very foundation of a cosmic object. The mechanics of a WIMP star hinge on a delicate balance. In the dense heart of these objects, WIMP would annihilate in pairs, transforming their mass into pure energy. But unlike fusion, which requires extreme temperatures and pressures to sustain, WIMP annihilation operates under different rules. The process is self-regulating. As the star's core heats up, the increased particle motion keeps collisions frequent, releasing energy that stabilizes the star against gravitational collapse. The result is a bizarre equilibrium where the star's size and luminosity are dictated not by nuclear reactions, but by the dance of dark matter at its core. What makes WIMP stars particularly tantalizing is their potential visibility. While they wouldn't emit visible light, the gamma rays produced during annihilation could escape into space, detectable by instruments like NASA's Fermi Gamma Ray Space Telescope. Similarly, the neutrinos generated nearly massless particles that travel unimpeded through the cosmos might be captured by sensitive detectors like Ice Cube in Antarctica. These signals wouldn't resemble the bursts from supernova or pulsars. Instead, they'd form a steady, faint hum, a whisper of energy from an otherwise invisible source. The hunt for these stars is already underway in the data. Astronomers are scouring gamma-ray maps for unexplained sources, patches of sky that glow faintly in high-energy light but lack a visible counterpart. Some of these anomalies could be distant WIMP stars, their gamma-ray emissions redshifted by the expansion of the universe into a barely perceptible flicker. Similarly, neutrino observatories are fine-tuning their searches to spot patterns that deviate from known astrophysical sources, hoping to catch the faint, rhythmic pulse of a dark star's annihilation heartbeat. The implications stretch far beyond mere detection. If WIMP stars exist, they'd be direct proof that dark matter can clump into structured objects, not just diffuse halos. This would revolutionize our understanding of dark matter's behavior, suggesting it's capable of forming complex systems under the right conditions. Moreover, their presence could explain some of the universe's lingering mysteries, like the origins of certain high-energy cosmic rays or the unexpected distribution of gamma-ray background radiation. Yet the challenges are immense. Distinguishing a WIMP star's signal from other cosmic noise requires unprecedented precision, and competing theories like pulsars or black hole jets could mimic their emissions. Future telescopes and detectors with greater sensitivity and resolution might finally provide the clarity needed. Until then, WIMP stars remain one of astrophysics' most electrifying what-ifs, a reminder that the universe's darkest corners might still hold surprises powerful enough to rewrite the textbooks. Among the many candidates for dark matter, actions stand out as one of the most intriguing ghostly particles so light they barely register, yet potentially so abundant they could shape the cosmos. Now imagine a star built not from atoms or even WIMP, but from these elusive actions, condensing into a celestial object that hums with quantum energy. This isn't just another dark star, it's a cosmic transformer, turning invisible particles into faint glimmers of light under the right conditions, offering us a rare chance to glimpse the invisible. Actions were first dreamed up to solve a puzzle unrelated to dark matter, the strange symmetry of the strong nuclear force. But physicists soon realized these hypothetical particles had all the right traits to explain the universe's missing mass. They're neutral, slow-moving, and barely interact with ordinary matter. In the dense heart of an action dark star, these particles wouldn't just sit idle. Packed together tightly enough, they could begin to behave like a single, rippling quantum wave, a phenomenon known as a Bose-Einstein condensate. Picture a star that isn't a fiery ball of plasma, but a swirling, ultra-cold fog of actions, bound together by gravity and quantum weirdness. What makes these stars truly extraordinary is how they might betray their presence. Actions have a unique trick up their sleeve. In the presence of strong magnetic fields, they can convert into photons, the particles of light. In the turbulent magnetic environment around a neutron star or black hole, an action dark star could flicker to life, emitting faint, telltale radio waves. It's like a cosmic lighthouse, but instead of shining through fog, it's revealing itself through a curtain of darkness. Astronomers have already begun scanning the skies for these signals, tuning radio telescopes to the specific frequencies action conversions would produce. The challenge is separating these whispers from the universe's background noise. galactic magnetic fields are messy, twisted by supernova and stellar winds, creating a cacophony of radio emissions. But action signals would have a distinct signature, a narrow, unwavering frequency that doesn't match any known astrophysical source. Projects like the Action Dark Matter experiment ADMX are refining their detectors to catch these precise tones, while radio observatories scour data for anomalies that could point to action stars lurking in the Milky Way's halo. The implications of finding one would ripple far beyond astrophysics. Action dark stars could solve two cosmic mysteries at once: the nature of dark matter and the origins of unexplained radio signals. They might even explain fast radio bursts, those enigmatic, millisecond-long pulses from deep space, if action stars occasionally rupture, releasing their pent-up energy in a sudden, brilliant conversion. Most tantalizingly, they'd prove that dark matter isn't just a passive backdrop to the universe, but an active participant, capable of forming structures as complex and dynamic as the stars we see. The search is a testament to human ingenuity, pushing detectors to their limits in pursuit of particles that might not even exist. But if action dark stars are real, they're hiding in plain sight, waiting for the right magnetic key to unlock their secrets. And when we finally catch that faint radio hum, it won't just be a discovery, it'll be a conversation with the universe's darkest corners, speaking in a language we're only just beginning to understand. What if some of the black holes we've catalogued aren't black holes at all? Beneath their event horizons, these cosmic enigmas might hide a secret. They could be dark stars in disguise, masquerading as singularities while operating under entirely different rules. The key to unmasking these imposters lies in their gravitational whispers, subtle deviations that reveal a truth far stranger than we ever imagined. Take the black hole at the center of galaxy M87, the first ever photographed by humanity. Its shadow fits Einstein's predictions beautifully, but what if there's more to the story? A dark star mimicking a black hole would bend light almost identically, creating a near-perfect illusion. The differences would lurk in the details. Unlike a true black hole, which traps everything behind an event horizon, a dark star might allow faint quantum effects to leak outward, a phenomenon called soft hair in theoretical physics. These barely their traces could distort the fiery ring around the shadow in ways our current telescopes can't yet resolve. Then there's the way these objects eat. Black holes are messy diners, shredding stars into glowing accretion disks that scream in X-rays. But a dark star might consume more quietly. Without an event horizon, infalling matter could pile up near its surface, emitting oddly muted radiation. Astronomers have already spotted a few black hole candidates that seem strangely underfed, their disks dimmer than models predict, as if something's intercepting the light. Could these be dark stars, their interiors resisting collapse just enough to alter the feast? Gravitational waves add another layer of intrigue. When black holes collide, their mergers produce signature chirps, sharp spikes in spacetime's fabric. A dark star duo might dance differently. Their waves could carry faint echoes, ripples bouncing off a hypothetical quantum crust instead of vanishing into a singularity. Data from LIGO's early runs already holds unexplained glitches. Could these be the fingerprints of dark stars crashing in the void? The debate isn't just academic. If even one black hole turns out to be a dark star, it would rewrite our understanding of gravity's extremes. These cosmic doppelgangers could be the missing link between theory and observation, proving that nature has more than one way to build a monster. The hunt is on to find them, not by looking for what's there, but for what isn't. After all, the universe's greatest deceptions often hide in plain sight. String theory paints a universe far stranger than the one we see, a cosmos woven from tiny, vibrating strands of energy, curled up in dimensions beyond our perception. Now imagine if dark stars aren't just hidden in our three-dimensional space, but are actually higher-dimensional objects, their true forms extending into realms we can't fathom. These wouldn't just be stars lurking in the dark, they'd be cosmic icebergs, with the bulk of their mass and structure tethered to dimensions we can't access, while their gravitational shadows seep into our reality. The math behind this is mind-bending. In string theory, gravity could leak into our universe from adjacent dimensions, explaining why it feels so weak compared to other forces. A higher dimensional dark star would exploit this loophole, anchoring itself in a realm with more spatial axes than our own. From our perspective, its gravity would appear amplified, as if the star were far more massive than its visible effects suggest. Picture a creature living on a flat sheet of paper suddenly feeling the weight of a sphere hovering just above it. The paper dweller wouldn't see the sphere, only the mysterious dent it leaves behind. That's how a higher dimensional dark star might warp our cosmos, invisibly, irresistibly. Clues to their existence could be hiding in plain sight. Some black hole candidates exhibit gravitational anomalies, tiny discrepancies in how they bend light or tug on nearby stars. These glitches might not be errors in our models, but fingerprints of extra dimensions. For instance, a 5-dimensional dark star's gravity would drop off faster than expected with distance, a subtle signature next-generation telescopes could spot. Even more tantalizing are gravitational wave signals with odd harmonics, ripples in spacetime that vibrate in ways our 3-dimensional physics can't fully explain. These could be echoes from collisions occurring partially in hidden dimensions, the cosmic equivalent of hearing footsteps through a wall. The implications rewrite the rules of astrophysics. If dark stars are higher dimensional, they might not even obey our universe's speed of light limit or thermodynamic laws. Energy could vanish into other dimensions, explaining why some cosmic events seem to lose energy mysteriously. Their formation would also defy conventional stellar evolution. Instead of condensing from gas clouds, they might nucleate like bubbles in a higher dimensional foam, pinching off into our space as gravitational anomalies. Detecting these dimensional refugees would require rethinking our tools. Particle colliders might create micro-black holes that evaporate too quickly, hinting at extra dimensions. Gravitational wave observatories could hunt for echoes in merger signals, reverberations from waves bouncing off hidden dimensional boundaries. Even dark matter detectors might pick up anomalies if higher dimensional particles occasionally tunnel into our universe. The most thrilling possibility, these stars could be portals. Under extreme conditions, their higher dimensional geometry might warp spacetime enough to create temporary bridges, wormholes to realms beyond our own. It's a concept straight from science fiction, but if string theory holds any truth, the universe's darkest corners might be its most connected. The search isn't just about finding stars, it's about mapping the hidden architecture of reality itself. Across the cosmic web, where galaxies cluster like beads on invisible strings, dark matter weaves the universe's hidden architecture. But what if these vast, diffuse halos aren't just passive scaffolding? What if they pulse with gravitational anchors, dark stars acting as the beating hearts of dark matter itself? These elusive objects could be the engines shaping the cosmos, their immense mass sculpting the distribution of galaxies and holding the cosmic web taut across billions of light years. Think of the universe's large-scale structure as a spider's silk, stretching and intersecting in a delicate, gravity-bound lattice. Simulations show dark matter pooling at the nodes of these intersections, forming dense knots where filaments meet. Now imagine dark stars nestled within those knots, their gravity amplifying the pull of surrounding dark matter, drawing in even more material like cosmic whirlpools. Over eons, this process could seed the formation of galaxy clusters, with dark stars serving as the invisible pivots around which visible matter organizes. Without them, the cosmic web might lack the gravitational hooks needed to gather galaxies into the intricate patterns we observe. Evidence for this role might be hidden in the peculiar motions of galaxies. Some galaxy clusters move as if tugged by something far more massive than their visible components, suggest a phenomenon known as the missing satellite problem. Traditional dark matter models struggle to explain these anomalies, but dark stars could fill the gap. If these objects formed early, their concentrated mass might have provided the extra gravitational glue needed to bind fast-moving galaxies into cohesive clusters. Even now, their lingering presence could be warping the trajectories of stars at the fringes of galaxies, creating the subtle orbital mismatches astronomers can't quite account for. The connection runs deeper. Dark stars wouldn't just influence structure, they might also regulate dark matter's behavior. In regions where dark matter particles are densely packed, interactions between them could generate faint heat or radiation. A dark star's core, brimming with annihilating particles, might emit just enough energy to stir the surrounding dark matter halo, preventing it from collapsing into an overly dense clump. This delicate balance could explain why dark matter halos maintain their smooth, diffuse profiles instead of crunching into black holes. It's a cosmic feedback loop. Dark stars shape the halos that birth them, while those halos in turn sustain the stars. The implications ripple across cosmology. If dark stars truly are the architects of large-scale structure, their distribution could hold clues to the universe's expansion, rate a current flashpoint in astronomy known as the Hubble tension. Their gravitational fingerprints might also shed light on why some galaxy clusters appear oddly puffy, with more space between galaxies than simulations predict. Even the cosmic microwave background, the afterglow of the Big Bang, could bear the imprint of dark stars' early influence, its tiny temperature fluctuations hinting at where these objects first ignited in the primordial darkness. Detecting their role won't be easy, but astronomers have a few leads. Gravitational lensing surveys could reveal excess mass concentrations, unexplained gravitational hotspots where no visible object exists. Future radio telescopes might catch the faint hiss of dark matter annihilation in these regions, a sign of dark stars churning at the heart of halos. And as simulations grow more sophisticated, they could pinpoint the precise conditions under which dark stars emerge as cosmic anchors, refining where we should train our instruments. The beauty of this idea lies in its elegance. Dark stars wouldn't just be celestial oddities, they'd be the silent choreographers of the universe's grand design, their gravity orchestrating the dance of galaxies across time and space. If we're right, these hidden giants have been shaping the cosmos since the beginning, their pull writing the story of everything we see and everything we don't. Deep in the cosmic void, where silence seems absolute, an invisible orchestra might be playing not with sound, but with space-time itself. Picture a network of dark stars scattered across the universe, each one a massive soloist warping the fabric of reality as it moves. Individually, their gravitational whispers are too faint to hear, but together, they could form a cosmic symphony, a background hum of gravitational waves so pervasive it vibrates through the entire universe. This isn't just theoretical poetry, it's a phenomenon scientists call the gravitational wave background. And if dark stars exist in abundance, they could be its unseen conductors. Gravitational waves are ripples in space-time, first detected in 2015 when LIGO caught the collision of two black holes, but those were the universe's symbols clashing, a sudden, explosive event. The gravitational wave background is different. It's the equivalent of a distant, continuous choir, a superposition of countless subtle waves from sources too numerous and widespread to isolate. Dark stars, with their immense masses and potential longevity, are perfect candidates to contribute to this chorus. Even if they never collide or explode, their mere motion orbiting each other, drifting through galaxies, or pulsating as they consume dark matter, would send out faint, persistent ripples. Over billions of years, these waves would overlap and combine, filling the cosmos with a gravitational murmur just waiting to be heard. The challenge lies in detecting this signal amid the universe's noise. Current observatories like LIGO aren't sensitive to the ultra-low frequencies of the gravitational wave background. Their instruments are tuned to higher-pitched events like black hole mergers. But upcoming projects aim to change that. The Laser Interferometer Space Antenna, or LISA, a planned space-based observatory, will float in orbit free from Earth's seismic disturbances, its arms spanning millions of kilometers. This vast scale allows it to catch waves with periods of years, even decades, perfect for picking up the slow, resonant hum of dark stars. Another contender, pulsar timing arrays, uses the universe's natural metronomes, rapidly spinning neutron stars called pulsars. As gravitational waves pass through the galaxy, they minutely stretch and compress space-time, subtly altering the pulsar's clockwork ticks. By monitoring dozens of these pulsars across the Milky Way, astronomers could piece together the wave patterns imprinted by dark stars. What makes this search so electrifying is the potential to map the invisible. Just as the cosmic microwave background gives us a snapshot of the infant universe, the gravitational wave background could reveal the hidden architecture of the present-day cosmos. Dark stars might cluster along filaments of dark matter, their combined waves betraying the skeleton of the cosmic web. Some models suggest their distribution could even carry echoes of the universe's early inflation, a primordial fingerprint preserved in spacetime's vibrations. And then there's the music itself. The gravitational wave background wouldn't be a monotone drone. Different populations of dark stars, primordial versus modern, isolated versus binary, would produce waves with distinct frequencies, like sections of an orchestra playing in harmony. A dense cluster of dark stars might generate a deeper, resonant bass, while rogue dark stars drifting between galaxies could add higher-pitched, wandering notes. Advanced algorithms could one day decompose this symphony into its individual instruments, reconstructing the locations and masses of dark stars purely from their gravitational echoes. The implications stretch beyond astrophysics. If we can decode this cosmic hum, it might settle one of cosmology's fiercest debates: how often black holes merge across the universe. Some of the waves currently attributed to black hole pairs could instead come from dark star binaries, subtly shifting our understanding of stellar evolution. It could even hint at dark matter's true nature, whether it's cold, warm, or something more exotic, by revealing how easily it clumps into stars. For now, the symphony remains just beyond our hearing, a ghostly composition woven into the fabric of spacetime. But as our instruments grow more sensitive, we inch closer to the day when the universe's darkest performers finally take center stage, not with a bang, but with a hum that's been playing since the dawn of time. From frozen dark stars hovering near absolute zero to mirror matter stars hiding in parallel dimensions, the sheer diversity of these cosmic phantoms stretches our imagination to its limits. Quantum dark stars blur the line between particles and waves. Spinning phantom pulsars broadcast gravitational rhythms across spacetime, and rogue dark stars drift unseen between galaxies like ghosts in the night. Each theory peels back another layer of the universe's secrets, challenging everything we thought we knew about matter, gravity, and the very fabric of reality. Consider the implications if even one of these dark stars were confirmed. A magnetic dark star could unravel the mysteries of dark matter's hidden forces, while a time-dilated dark star would put Einstein's relativity to the ultimate test. A WIMP-powered star might finally reveal dark matter's composition, and an action star's radio whispers could open portals to quantum realms we've barely dreamed of. The discovery wouldn't just add a new entry to the astronomy textbooks, it would rewrite them entirely, forcing us to rethink how stars form, evolve, and shape the cosmos. The hunt for these objects is already pushing our technology to its limits. Gravitational wave detectors listen for the faint hum of spinning dark stars. Neutrino observatories chase invisible particles from their cores, and next-generation telescopes scan the void for lensing distortions that betray their presence. Every unexplained anomaly in our data, every gravitational hiccup in a star's orbit, could be the clue that leads us to the ultimate cosmic hide-and-seek prize. But the most thrilling part, this isn't just about filling gaps in our knowledge. Dark stars represent something far grander, the untapped potential of the universe. They remind us that reality is far stranger than our theories dare to predict, that the darkness we've long dismissed as empty might be teeming with hidden architecture. From shaping galaxy clusters to birthing black holes, these invisible giants could be the silent architects of everything we see. So which dark star captures your imagination? The frozen relic drifting between galaxies, the vampiric binary feeding on its visible twin, or the higher dimensional enigma warping space-time itself? Drop your thoughts below, and if you're hungry for more cosmic mysteries, hit subscribe. The universe's darkest secrets are waiting, and the next breakthrough could be just one observation away.